There are two goals for this webinar. Clearly, we want to demonstrate Maple's ease of use tools for course in differential equations. With this paradigm, the course material is taught instead of the tool being taught. And then we want to demonstrate a pedagogy in which the use of Maple generates insights over and above what can be done with the traditional tools of pencil and paper. This paradigm appears in the literature under the guise resequencing of skills and concepts, and puts the development of concepts before the mastery of manipulative skills. Early on in a differential equations course, the notion of a direction field appears. Let's see if Maple provides any help with drawing and interpreting direction fields. I'm going to make use of a task template. All right, tools, tasks, browse, table of contents comes up, tasks, differential equations, ODEs, direction field. Here's your task template. It can be inserted by clicking either of these two insert buttons. Default content, you get the extra verbiage. Minimal content means you get enough to make the thing work. I've got the task template embedded already. Here's the path to it. What we have to do is get this right-hand side here. So I think I'll just copy that right-hand side to the clipboard, Control-C, and then use the Tab key. It auto-selects that right-hand side. I'll paste our differential equation, right-hand side, hit the Enter key. Now this task template knows what the differential equation is. I'll keep the size of the window 0 to 1, 0 to 1. And now notice that a command is being executed. Next time I hit the Enter key, DE plot in the DE tools package. And notice the equation labels. The data in these first 3 lines is captured and referenced by these equation labels. So by putting in these equation labels, all I have to do is hit the Enter key, the data gets entered. This is a piece of the direction field for this particular differential equation. Now, if you put a list of initial points, notice they all start at 0, so I have initial points along the y-axis. Hit the Enter key, I'll use that list, and re-execute the command including that list of initial points. Then you get the direction field and integral curves emanating from those initial points. Another concept that appears early in a differential equations course is that of the Nullcline and the isocline. They're basically graphing ideas. So the Nullcline is the curve, planar curve, along which the derivative is 0. So we're looking at x squared plus y. So let's select that. I'm going to hold down the Control key and drag that. It's equivalent to copy-paste. It's not a Maple thing. It's a Windows thing at the moment, and it can be done in other operating systems as well. We're looking for where that curve is 0. Or that expression is 0. So here in the context panel, I'm going to go down to plots and pick implicit plot, 2D, variables in the order x, y. There is the Nullcline. It's the curve along which that derivative is 0. Isocline is the curve along which the derivative is other than 0. And there are 2 different ways you can look at this. You can look at the derivative expressed as x squared plus y. Here, I think I'm just going to type that x squared plus y. We're looking at that as a function of 2 variables. We can draw it as a surface. So we could go here to plots and pick 3D plot with the variables in the order x, y. You can also notice up here you have the option, if you click that button, you would also get the 3D graph. Well, you can interact with this. I like to look at it this way. You can add to that by right-clicking. I change the style, and you can make it a surface and a surface with contour lines. So now you see the contours. If you draw a contour map by looking at it from above, okay, these lines projected down into the XY plane are the isoclines. And if you want to see how they change the value along the isocline changes, just tilt this up, and you can see as you go up on the sides of the surface, the value of the derivative along that curve is a constant, and the constants increase. Now, you can also look at this directly as a 2D contour plot. X squared plus y is easy enough to type. Go over to the plot builder, so plots, plot builder, and we are drawing a 2D contour plot. And so now you have some control over what this contour plot will look like interactively through the plot builder. So isoclines, nullclines, graphical items, and clearly Maple will draw those graphs, allowing a study of what these curves tell you about the differential equation without having to struggle to draw the graphs. What about Picard Iterates? If you're going to prove one of the basic existence uniqueness theorems using Picard iteration, it might help to have an idea of what is a Picard iterate, how does it work. So here is a task template. I showed you what the task templates are. Here is a task template for obtaining Picard iterates. Here's a differential equation. This is x squared plus y with an initial condition because it's an initial value problem. Again, we want to get this into the beginning of, so we can do a copy into the beginning of this task template, hit the enter key. Okay, so Maple now knows the differential equation. The initial point, x0, that's 2. So let me tab over here and put a 2, hit the enter key. An initial iterate, I'm going to take 1. So let me tab over here and type 1, hit the enter key. Number of iterates, 3, 4, 5. I'll try 5. Hit the enter key. Now there's some code here, and you can see that there's an integral of phi k in f, and that gives you phi k plus 1, and a few lines of code to print out neatly what we're computing. So I just hit the enter key, let Maple do its job, and you see you have a number of iterates. These iterates would become a lot more meaningful if we could compare them to the exact solution. Well, how hard would that be? Well, you need the exact solution. So to do that, you want to have Maple solve the differential equation along with the initial condition. So that's an initial value problem you want Maple to solve. So it's this differential equation. I think I'll just copy that. And the initial condition is y of 2 equals 1. So here is the differential equation. Put a comma, y of 2 equals 1. So there's the differential equation, initial condition. So you have an initial value problem. Let's go over here to the context panel. We have solved the DE for y of x. So we have a solution. In order to draw a graph, you want to pick off that right-hand side, so let's just grab right-hand side. Now it's a question of drawing this graph, so I'll make use of the plot builder to do that. So plots, plot builder, 2D graph. The advantage here is that I can more easily control the domain. And I want to go from 2 to 5. So the default is minus 10 to 10. And I want to go 2 to 5. Okay, so there is a portion starting at 2, going ahead a bit. Exact solution. I want to see how these iterates compare. I'm going to take the first and the last. So I will just do a copy and paste. So you can see it starts out near 2. That iterate is close, but it shortly is not close. I'll just grab this last one, copy and paste. Much closer for longer. Okay, so you can see how the iterates start to converge to the solution, and that's a key step in the proof of existence uniqueness based on Picard Iterates. You can get some insight into what Maple is doing under the hood while it's solving a differential equation. It has to classify them to figure out what part of the algorithm to hit it with the appropriate code. You can access that with a task template. Here's the path to the task template. This is the default setup for the task template. What we want to do is we want to get this differential equation into the first slot. So I'll do a copy, tab over here, do a paste, hit the enter key, and you see there is a command, ODE advisor, in the DE tools package, which is going to execute when I hit the enter key, and it tells me, oh look, this is a Bernoulli equation. If we raise the info level on the command dsolve, you hit pre-programmed breakpoints that will give you some information while dsolve is acting, and then I've set it back down so that it wouldn't continue to affect the rest of the computations. So as Maple solves this particular differential equation, it comes up with this solution. You can see what it's gone through. It has to classify first, so a quadrature, linear first order, try Bernoulli. Bernoulli was successful. This classification functionality can also be reached through the context panel. So we need a differential equation. So let's do a control drag here. And then up here it says classify the ODE, y of x is the variable, and we get the help page for how Maple will solve a Bernoulli equation. So the classification is Bernoulli equation, but the help page for solving a Bernoulli equation pops up, and so you get this additional information about how Maple goes about solving the equation, and there are the steps that you could go through to imitate or do the Bernoulli solution stepwise. A significant chunk of the differential equations course is devoted to the second order constant coefficient ODE, the initial value problem that it captures. This differential equation is the equation of motion for a damped oscillator, and it's driven. So let's take a look at this initial value problem. There is a tool called the ODE Analyzer Assistant. Tools. Used to be up here in the Assistants. It has been moved down and classified as a tutor. This ODE Analyzer Assistant is now in with the tutors. To make use of that, the simplest thing to do is bring the differential equation down. I'll do a control drag there. And go to the context panel where you see two relevant items. Solve the DE. You'll get a general solution with two arbitrary constants. And solve it interactively. And that's going to bring up this assistant. And the differential equation is now already in it. Let's add the initial conditions. Y at 0 I've taken to be 2, as you can see. You add that. Ooh, I have to Y at 0. I guess you need a tab there to get over to the 2. Click the add. Then this is a drop down, so you go Y prime at 0, and that would be the -1, I believe. Add that. Click done. We now have an initial value problem that can be solved numerically or symbolically. Clearly it can be solved symbolically. Here is the solution. That solution can be seen in the bigger window, so easier to read. The graph can be obtained by clicking the plot button, and you have a graph of y. You could see a little bit more than that if you go to plot options. Make a copy of y. Change that copy to y prime. Click done. Now when you click plot, you get a graph of y and y prime. This checkbox displays the command for solving the equation, dsolve, and the command for drawing the graph. So if you are interested in learning the commands, there is a way. It's much easier at the beginning of this section of the course to use this tool to get the solution. You can see what its properties are, draw the graph, see what its properties are, before worrying about what is the syntax by means of which you do this. So you can put the concept first, emphasize that, worry about developing the manual skills later, and upon quitting, you can get the graph or the solution or the Maple commands, whatever. Let's put in the solution. So we'll click quit, and we've got the solution. A stepwise implementation of this solution would run something like this. I've got some commands typed here to speed this thing up. Here is a notational adjustment. Here's the differential equation, the initial data. This is the solution that we just obtained. Here is the graph. So I've just reproduced the information that we obtained from the assistant. Now let's do a stepwise calculation. We begin by finding a fundamental set. How do you get a fundamental set? You make the exponential guess, which is e to the lambda t. You put that into the homogeneous differential equation, factor out the common e to the lambda t. You've got the characteristic equation. Solve the characteristic equation. There you have the characteristic roots. For each root, you get a solution, but these solutions are complex. How do you make these solutions look like the members of this fundamental set? Well, you use superposition. You add and subtract. One you add and divide by 2. One you subtract and divide by 2i. Those are the real solutions that you see in the fundamental set. Now you need a particular solution. This is the particular solution commands in the DE Tools package. That allows you now to ask, where did that come from? Well, you have two choices. You can use a variation of parameters, or you can use undetermined coefficients. I'm going to use undetermined coefficients. What is the template for the undetermined coefficient calculation? It's this. What do you do with it? You put it into the differential equation, and you say this now has to be an identity in T. So you can go that route and say solve that equation as if it were an identity in T, and solve it for A and B, and you get those two values for A and B. When I first learned this years and years ago out of one of the editions of Rainville, what you had to do working by hand is collect like terms, and then coefficients would have to be 0. So these are the equations that I would have written down years and years ago. You solve those, and you get the same two values for A and B. So that says you've got a particular solution. Now you can construct a general solution, but that introduces two new constants, right? There's a homogeneous solution, particular solution. How do you solve for the two new constants you just added to the problem? You use the initial data. Now, this code here goes up to where the initial data was stated, grabs the right numbers, puts them in place in the appropriate equations. You have to solve those two equations. You get these two values, put them into the solution, and then there should be one more step. Compare that to the D-solve solution. They should be the same. If they're not, you got to ask, what happened? Okay, so you can see that the algorithm, by means of which one of these initial value problems is solved, is complicated. There are many steps, about 15 steps. If you make an arithmetic mistake in any one of them, you wander around forever with horrible algebra and get very frustrated. So, by using Maple to go through these steps a couple of times, you can see how all the pieces fit together. At the end of which, as you start to move away from Maple to learn the manipulative skills that you probably want your students to have, they at least have a template in the back of their heads. It's in their minds now how the steps fit together and how the algebra is supposed to work out. If not in a first course, then certainly in a second course in differential equations, the first order linear constant coefficient system will be studied. So here's a problem of that type. Here we have a system, 2x2 system, initial data. We have some questions that we want to ask about this. Let's begin with a solution from the analyzer assistant. Well, to do that, we'll control drag both equations, make a sequence of the two equations, and launch the assistant from the context panel. Solve the system interactively, and here's where we can enter the data. X at 0, 3/10. Add that in. This now becomes Y at 0, and I've chosen 0. Click Done. And here is a initial value problem. It can be solved numerically. This can be solved symbolically, so let's have Maple do that. There's the solution. You want to see it in the bigger window. You can see X of t here, Y of t. But notice that you have linear combinations of the same two exponentials, e to the 7t and e to the minus 9t, in both x and y. For graph, this is a graph of x of t. And look at these great big numbers. And the reason why is, look, you have e to the 7t. T is out here till 10. big numbers. So we want to make some adjustments. So let's not let t be any bigger than 1. And let's make a copy of x and change that x to a y. So when we draw the graph, we have curves x of t, y of t. We can also change the horizontal axis to x, remove that from the functions that are going to be graphed, and when we click plot, that's one orbit in the phase plane. Here you would see the commands, and on clicking quit, we could get back solution, plot, commands. Let's get the solution back. Okay, so there's the solution via the ODE Analyzer Assistant. To get a phase portrait, we'll make use of a task template. You've seen where the task templates are stored. Here's the path to it. Plot window, where at the moment guessing, try minus 1 to 1 for each dimension, minus 1 to 1. We need the differential equations. Well, we can control drag them, or we can type them. It'll be very fast to type in 3x plus 12y here, and here it's 4x minus 5y. Now we need the equilibrium or critical points, which there's only one. It's 0, 0. And the integration parameter along each trajectory. We're going to integrate in both directions, or the integration will be numeric. I'm going to run minus 3 to 3, so for each point that I want a trajectory to go through, I want to integrate both forward and backwards. So when I click this button, Maple draws the chunk of phase plane, puts in arrows to show which way the trajectories are being traced. This green dot is the equilibrium point. If we click on a point, we get a trajectory drawn through that point. So if we put in enough trajectories, we should get a sense of what kind of equilibrium point this is, and we see from the phase portrait that we're constructing, it appears to be a saddle. The solution to this system can also be obtained by finding a fundamental matrix. So to do that, we need to define the system matrix. So we'll go here to the matrix palette, insert a matrix. The numbers you can read from the differential equation: 3 tab, 12 tab, 4 tab, negative 5. I want to give that the name A, so let's go here to the context panel, assign to a name. Let's use the name capital A. So now we have the system matrix. Write that name, press the enter key, go over to standard operations in the context panel, matrix exponential. We want the variable to be t, e to the at. You have this matrix. It's not as simple as it could be, so let's simplify it. First we'll do an expand. Here we go, expand. And then we'll do a combine. Where did that go? Combine. Okay, so that's about as simple as you're going to get it. And now I want to give this a name. Typically the name is phi. So assign to a name, and here we type PHI. fundamental matrix. How do you get a solution after you've gotten the fundamental matrix? Well, you multiply the initial vector by phi. So phi, period for non-commutative multiplication. Simplest way to get this initial vector here is simply to put in angle brackets for which are inequality symbols. 10/3 or 3/10. 3/10 comma 0. Now that solution should be the same as the one that we got up here. How can we compare? Well, we could copy this and paste it in and then compare. Here's a copy. Paste. So this first component of this vector is x. You look here, it's x. Second component is y. Compare here, it's y. However, the solution that you find in almost every DE textbook at this level is by Eigen Pairs. So we have the system matrix A. It's already been done. We don't have to do it again. There's A. We want its Eigen Pairs. So go to the context panel. You have eigenvalues, etc. Let's select eigenvectors because that gives you the eigenvalues as a column vector, and then the columns of the matrix are the corresponding eigenvectors. So I'm going to grab that matrix of eigenvectors, select element 2, and then I want to split that into columns. So I believe it's here. Split into columns. So I have a list of 2 column vectors. Each one is an eigenvector corresponding in the order you see here to the eigenvalues. I'm going to give this a name, assign to a name, and I will use uppercase X. So I can reference the first x and the second x as the 2 eigenvectors x1, x2. So the general solution can now be written. It's A space for implied multiplication. Then we need an exponential e. Typing an e doesn't do it. You can get it here from a palette. I've got e in my favorites palette, which I got in there by finding it in someplace else, like common symbols, right-clicking, add to favorites. So that's one way to get exponential e. Lambda 1, that's -9 t. Right arrow key to come down, plus b space. Now another way to get the exponential e is you type in e and press the escape key. That gives you a list of things that begin with e, and you notice the very first one is exponential e. That's another way to get the exponential e. So that's to the power 7t. Right arrow key. I didn't put in the vector x. So let's put a space here. X sub 2, that's the second eigenvector. Let's just come back over here and do a quick edit. Space x1. Okay. This is our general solution. We're going to give it a name y. Now, we need to apply the initial data in order to determine a and b, little a and little b there. So, at t equals 0, we want to substitute into big Y. that vector has to be the initial vector. Well, we want to be able to reference this vector, so let's call that y0. Okay? So y0 and the vector 3/10 0 have to be equated so that this equals that and this equals that. So there's an equate option which gives us two equations where the components of these two vectors are set equal to each other. Send these equations over to solve. The simplest solve will work. There are the values of a and b. If we put them back into y, we'll get not the general solution, but the specific solution to this problem. So let's do a substitute into, and we're substituting into y. That, again, is our solution, and if we want to compare that to one of these other solutions here, let's grab this one. I'll do a copy and paste it right under, and we can see whether or not these are the same. Just the fractions are written slightly differently. I think they're the same. There's another tool in Maple's toolbox that's worth knowing about. Suppose we use this tool to explore the Lotka-Volterra predator-prey model. It's a differential equations tutor. Remember, tools, tutors, go over to differential equations. It is this one called DE plots. I will launch it from this button. This is what it starts out as. It has a number of built-in models, the Lotka-Volterra model being one of them. And click on DE plot, and that brings up this window. Here's the model, it has parameters. You can set values for the parameters here. You can pick initial values here for these orbits to be drawn. They don't close because t needs to be increased. I think going to about 14 will do that. Okay, so now you have closed orbits. The number of arrows can be modified, and their shape and size can be changed. Any other options you might want to put in, you can insert here. Now, if you go back and select animate, then you get an animated version of the orbits being traced. So it follows the arrows. Okay, so quick look at this tool. I believe if we click quit, we come out of the tool. And a simple way to access a variety of models, play with them, see how they behave, learn something about the model before digging in at a more fundamental level of how do you extract information from the model using first principles. Example 8 looks at a nonlinear autonomous system. It asks these questions. Find the equilibrium or critical points, then sketch a phase portrait, and then linearize and analytically determine the nature of each critical point. By way of solution, let's see what Maple has to offer. To find the equilibrium points, make a list of the right-hand sides of the two differential equations, because we want to solve for where these right-hand sides are simultaneously 0. So here's a list. Like control drag to do that. Hit the enter key. Then using the context panel, solve using the simplest solve option, 4 solutions, and assign to a name, give it the name S so that we can refer back to these solutions as S1, S2, S3, S4. To obtain a phase portrait, we'll use the same tool that we used in example 6. It is this task template, and here's the path to the task template. We need to decide on the window, the viewing window. Well, let's look at these solutions here. The smallest x is 0, so let's start here at -1. The largest x appears to be 6, so let's go as far as 7 here. The smallest y is 0, so let's go from -1. The largest y is 5, so let's go to 6. Then we need to get these right-hand sides into the 2 boxes for x dot and y dot, and I'm using a control drag approach here. The critical points, they must be entered as lists. So 0, 0 is the first one, 0, 5 the second one, 6, 0, and finally 3, 2. Okay, then we're going to integrate numerically, going forward and backwards. I think -3 to 3, and we enter the data. We have a portion of the phase portrait. You can, or the phase plane here, you can see the arrows. For the direction field, the green dots are the equilibrium points, and then we click on points, and trajectories are drawn through the points that we click on. We put enough of these trajectories in, we should be able to guess at what these equilibrium points are. This appears to be a node out. This appears to be a node in. This appears to be a node in. And this appears to be a saddle. To linearize and determine analytically the nature of these critical points, we'll do the following. First, we're going to bring in the student linear algebra package. And we know how to do that. Go here to Tools, Load Package, and select Student Linear Algebra. Okay, then equation label 1 refers back to this list of the right-hand sides of the differential equations. So control equal has Maple echo back what that list is. In the context panel here, we select Jacobian matrix, and we get the Jacobian matrix, and we give it the name JM for Jacobian matrix. Then I make use of the evaluation template. I've got it right here in my favorites palette. You see it's stand-in for the eval command. It's in the expression palette here, and you get it into your favorites palette by right-clicking, and you have the option to add to favorites. That's how I populated my favorites palette. Okay, so evaluate this Jacobian matrix at the first solution, S1. Then it comes back with this matrix. The diagonal elements are the eigenvalues. They're both positive, so that first point is a node out, sometimes called a repeller. Do the same thing at the second point. The diagonal elements are again the eigenvalues. They're both negative, so that's going to be a node in. This is sometimes called an attractor. For the third point, the eigenvalues end up on the diagonal. They're both negative, so it's a node in, called an attractor. And for the fourth point, this one here, the Jacobian matrix does not reveal the eigenvalues immediately. So we go here to the student linear algebra package and select eigenvalues. And here you see the two eigenvalues. This one is clearly negative. The square root of 73 is greater than 7. So this one is positive, so the eigenvalue is positive. One positive, one negative. Therefore, that fourth point is a saddle. Here's a problem that would come up in a more advanced course in differential equations, but it shows up in Maple primes, the Maple form, more than once. I've treated it in my advanced engineering math book. Perturbation problem, regular perturbation. Now, when they showed up in primes, Maple Math posted this solution. It's a coded solution. It requires coding. I would like to show that this solution can be found syntax-free. Now, there's an advantage to coding. It's reproducible, easily changed, but there's an advantage to being able to do it syntax-free because then you don't have to know what all the commands are. Here's a visualization that would help us understand a little bit better what we're really doing. I have a slider that controls the value of the perturbation parameter p. So now we take a closer look at this particular differential equation. It's a third order. Here's the perturbation parameter p. Data. It's initial data and a boundary condition. Want to know how the solution varies with p. So this slider controls the value of p. This is a perturbation solution that we'll compute shortly. And this is a numeric solution, which is about as exact as we're going to get it. So you notice for small values of p, the two solutions are close. As p increases, the solutions separate. For small values of p, the region for which the approximate perturbation solution is usable is greater than it is when you increase the value of p. And you notice that as p changes, this quote exact solution in red moves also because the value of p is changing. And p influences the solution of the differential equation and the initial value problem that's built on it. Here's our syntax-free solution. I think I'll close that, make some space, close that for now. Now I've got a lot of this stuff typed in because that's just going to be faster. So here's the differential equation. I use the context panel to assign it to a name, right? Assign to a name. Gave it a name DE. I write the perturbation solution. A of x, b of x, p, c of x, p squared. Okay? Now, if you go back to this coded solution, what Maple Math did, see here's p, right? He's using his differential equation. He's using the syntax diff. Here is the perturbation solution. He's adding b0, b1, b2 as the coefficients. So he's subscripting. So that makes it easy to increase n if you understand all of the syntax. Okay. and then he plugs that into the differential equation, which is what we're going to do. So here's our perturbation solution. So we write y equals that perturbation solution. And we do a substitute into. You've seen me use a substitute into. We substitute into the differential equation. We get this much. Okay? Then we go to the context panel and we pick series. And we get a series in P. That's what this part is. Then we want to pick off the coefficients of P. So we use this coefficients, pick off the coefficients of P. And notice you get a sequence. There's one member of the sequence, there's the second member, and there's the third member. And I give that sequence the name Q. Q1 is the power p to the 0 coefficient. Q2, power p to the first. Q2 is p squared coefficient. So Q1, we have it's a triple prime. We set that equal to 0. We add the data. And notice that the data, initial value, and it was a boundary value. So I use the boundary value here on A. Then I solve that differential equation, right? You have a solve DE here, solve the differential equation. You get A of x equals x squared over 10. And I make that a function. Like a sine function. And I do the same for B and for C. So Q2, but only here I make the boundary condition be homogeneous because it's being the non-homogeneous part is being taken care of by A. So I get a B, I get a C, doing exactly the same steps. So having assigned made those functions A, B, and C, if I simply type f of x and do a control equal, I will get the perturbation solution written down. And that's the perturbation solution I used in that visualization. I computed it on the side and stuck it back up into that visualization. Okay, so a rather complex problem you can solve with point and click techniques. There's an advantage to this coded solution. There's a disadvantage. You have to know all of these commands. On the other hand, you can do it point and click. You don't have to know all of the commands.